What's up? This is Mars, and this is Lab 2, Motion of a Falling Object. The purpose of the lab is to analyze real-world versus computational characteristics of a falling object. And to do that, we observed a falling object in real life and then tracked those data points, predicted an object's movement with a computational model that includes the effects of gravity, and then altered that computational model to include gravity and drag, and then discussed the differences between those three. We used the Python simulation, real-world paper, Excel and graphs, the momentum principle, position update formula, as well as drag. The predicted path with only gravity was below the observed path, and the path with gravity and drag was a bit above the observed, but a lot closer, and I'm going to tell you why that is. Some initial knowledge I came with into this lab was, of course, the momentum principle and Newton's second law, and then here's how I derived that for computational lab purposes. So final velocity equals the initial velocity plus F net over m times delta t, and then having that position update formula to track through the while loop of the computational part of the lab, and then finally adding that drag formula. So the force of the drag is the drag constant times the ball's velocity, the magnitude of the ball's velocity squared times the ball velocity. Starting out with our initial conditions, the system is that paper ball around 6 centimeters in diameter, and then the surroundings are the air and my hand and the table. I took the paper ball and dropped it from above my head until it fell on the table. I took that video into Tracker and gathered the position over time values. And I took those values and put them into Excel to start creating my final graph, as well as got that initial time and initial position of the ball. And then I calculated the initial velocity by using the F-net from the computational model and found that, as well as using this drag formula and then found a B value for drag. I took all the values I gathered, so the ball's mass, which is about 5 grams, and then gravity, which is 9.8 meters per second, the initial position of the ball, which I got from the data earlier, the initial velocity, which I calculated, the delta t, and then the initial time, and then the F-net vector. So F-net, I couldn't just fill that vector in, so I kind of just showed you what I did here. So I changed the ball's velocity and did all of those changes, and then here I added the force of gravity, the force of drag, and then had a statement where F-net just equals gravity, and then F-net equals gravity plus drag, and changed and just commented each of those out. Again, I added that drag stuff, like I said in the last, and as well as that B value for drag. And finally, I added in those equations I talked about earlier. Finally, I checked to make sure the simulation matched up with the experimental as much as it could to make sure my work was right. And now we get into the results. So I took all of those values I had, right, and then put them all on this graph of observed versus predicted time. That gray line there is your gravity and drag. That blue line is the observed, and then that predicted with just gravity is that orange line that you see there. You can see that the predicted and the observed are fairly close, but the drag actually lines up a lot closer to the points on the top than the gravity does, although drag seems to have more of an effect as it goes down the graph. However, the position difference here is probably like 0.2 meters, which is fairly good. So it definitely could have, source of error definitely could have came from like my human error just in Tracker, and the real world cannot be calculated 100% with 100% accuracy. So that drag value could have been a bit different, or the equation we use couldn't have been exactly right, because it's really hard to calculate the force of an error, especially on an object that has a bunch of, since this was a ball of paper, this object has a bunch of like nooks and crannies that the air can kind of get trapped in and create more of an effect. So all of the models could predict a terminal velocity, that's that highest velocity before it goes down. The terminal velocity happens when the force of the drag exactly balances the force of gravity pointing down. This means for the net force, like that's when the net force begins to be negative on the object. If the object was initially flown downwards or just dropped from rest, like if the initial velocity is 0, that means it would have like traveled very quickly going down and then slowed down instead of, so like the exponential graph would kind of be flipped on the, still in the x quadrant, but just flipped.